Hello. So in this lecture or module, we are going to talk about very important topic that is called as intensity of an electromagnetic wave. So in the previous model, we explained and we talked about the EM wave energy of an electromagnetic wave. But now we are going to talk about the intensity of electromagnetic wave. So what is an intensity? So intensity is defined by S, and it is equal to the total power per unit area. So power divided by area. So imagine you have a sun and it is radiating an energy, okay, and we have a earth, and that radiation comes to earth, and we can actually, when we in a sunny day, when we go out, we can feel the warmth. So that radiation falling on our skin, on falling on our plants, animals, everywhere, we can see that it's a hot day, cold day, or so on and so forth. But how to express this concept mathematically? For example, if I use a magnifying lens, put in between the sun radiation and the object here on the earth, the intensity will get magnified when the sun rays passes through this lens. So let us define this concept with mathematical terms. So the formula here will be S is equal to power divided by area. So we can write that P per unit area, and we know that power can be written as energy per unit time divided by area. So power is energy per unit time, and we already know what is the energy of an electromagnetic wave. Please refer to the previous model. We can further expand this equation, and we can write that energy is nothing but energy density multiplied by the volume. And energy density is nothing but the strength of electromagnetic field multiplied by the volume, and the time divided by time per unit area A. Okay, and in the previous model, we have defined energy density is U. We have got the whole calculation and the derivation for this term. Please refer to the previous model. So it will be U, which is energy density multiplied by the volume divided by A times T. Time is T, area is here, and U is energy density. So we don't know what the volume is. So let us try to understand this concept. So imagine you have this electromagnetic wave with a specific amplitude and specific wavelength, and it is traveling into the space with the speed of light c. And this electromagnetic waveform is coming over a piece of volume indicated by this figure. So now this is a cube. It has a cross-section area is A, and it has a length L, which is equal to how fast the wave is coming to this volume, which is the C, constant C, multiplied, and in what time period it is coming and hit this object. So it is length of this volume is C times T. So we can write that volume is equal to area multiplied by the length, which is equal to A into C into T. So we just plug the value of L here. So once you know that, you can actually, this is the L, this is the S, which is the intensity S. We can take the value of the volume and plug it into this equation. So S can be written as U times A times C times T divided by A times T. So T gets cancelled, A gets cancelled, and finally we are left with U multiplied by C. So intensity of an EM wave is defined as the energy density U multiplied by the speed of light. Now we can further expand this expression. We know that since U is equal to half epsilon 0 E square plus half times mu naught times B square. So we can write that we have derived this expression in the previous module. This is the expression for the electromagnetic energy density. The density consists of the energy density of electric wave plus the energy density of magnetic wave. So we can further write this expression as equal to put the value of E here. So U here, epsilon 0 E square plus 1 over 2 mu naught B square multiplied by C. So this is the expression. And we know that also, since 1 over 2 epsilon 0 E square is equal to 1 by 2 times mu naught multiplied by B square. So we know that energy density of electric field is equal to energy density of magnetic field. So therefore we can write S is equal to epsilon 0 E square multiplied by C, or S is equal to 1 divided by mu naught into B square multiplied by C. So you see that these two parts are equal, this and this part is equal. So you can just plug in this value in this expression and you can represent S is equal to either in this form or S is equal to in this form. Okay, so remember the expression intensity of an EM wave will be given by electric field component multiplied by the speed of light C multiplied by the permittivity of free space, or in terms of magnetic field we can represent it through this expression. So these two important equations needs to be remembered. Now we have to understand through an example. So let us have an example here. The example is, let's imagine you have this sun and this is your earth. And we know that sun emits the radiation in all the direction. And some of these radiations, as shown over by these lines, falling onto the earth. They are coming under the earth. So we want to know what is the intensity of these radiations, of these signals, and these radiations are nothing but our electromagnetic wave. So there are questions to understand. To answer this question, we need to calculate what is the total output power of the sun, and based on that we'll be able to understand and calculate the intensity of EM wave coming on the surface of the earth. So let us frame the question. So question is, what is the total power output of the sun? What is the total power output of the sun? And the given parameters are, what is given here? We are given the intensity of sun at the earth. Intensity of the sun at the earth. Let's define it as SEARTH, earth. That's the number, let's say 1390 watt per meter square. So it says that the rays those are coming on and falling onto the surface of the earth, the intensity of those earth is about 1390 watts. So approximately 1.3 kilowatt per meter square. So on the earth area, which is square meter, in 1 square meter area of the earth, this much is the power that is coming to the earth from the sun. And what is the question here? We have to determine the total power. How much is the total power? So of course we are at the earth and we want to know what is the power at the sun. So to understand this question, let me draw this figure in this way. Let's say you have this sun over here. This is your sun. And let's say imagine you have this earth here, sun, you have this earth here, okay? And all these waves are being emitted right here. You can see that. And we say that the distance between the earth and the sun is indicated by a capital R. So that's the distance between sun and the earth. Okay. And let us draw the sphere. Let us draw the one sphere which will talk about the circumference of the earth around the sun. So let's say this is the area. Let me draw it in a good fashion right here. Yeah. So imagine this is your sun. Okay, and that's your circumference, total circumference. You can, and let us call it as A of the earth, circumference of the earth. So this is the sphere, and that's the radius. Okay. So now let's come back and try to solve this. So the answer would be, so we'll say that at the earth, S, that is the intensity. We know the formula, power, like right here. We have the formula here. Is divided by the area. And this is the value we are given, 1390 watt per meter square. So imagine this is the value. The intensity is the given. Now total power is to be calculated. Total power, P total, is to be calculated. So what is going to be the power? Power is simply this one, which is S times area. Just take the value of S, multiply it with the area. And what is the area? Area is nothing but the area of this sphere. That is the area of the earth surrounding the sun. So we'll say that this is the A sphere, area of the sphere. Let me correct this. This is your area, circumferential area of the sphere. Area. Okay. So, and what is going to be the value of A sphere? It is S times 4 pi r square. So area of the sphere is nothing but 4 pi r square. R is the radius. So can we plug in the values here? Yes, 1390 is the value of S multiplied by 4 times pi multiplied by r. What is the area What is the radius? R. This distance is known to us. So it is 1.5 into 10 to the power 11 the power square, not the power, is the square, R square. Okay, so the radius, which is nothing but the distance of the earth from the sun, this is the fixed value. And that comes out to be 3.93 into 10 to the power 26 watts. So this is the total power of the sun, and based on that we can calculate the intensity of the rays or intensity of electromagnetic waves coming at this earth, knowing the area, or if we know the intensity we can calculate the power, or vice versa. Now we calculated the we know the intensity of the sun at the earth's surface, which is this number. But what about the intensity of the waves at the sun's surface, right here at the sun's surface? Can we calculate that? Okay, so that was SEARTH, S earth. This is S earth. The rays coming at the earth, we can know the intensity of that. It's just 26, 10 to the power 26 watts. So it's, you can say it's a huge, it's a very high intensity waves that are coming onto the earth. Okay, 10 to the power 26, this order high. But what about the intensity of the electromagnetic waves or the rays at the sun's surface? Can we calculate that? Yes. So let us calculate that. So here we'll write that now. Let's calculate intensity S at the sun's surface. So we can define it as sun. And that is, again, intensity is nothing but P total, power total, divided by area of the sun. Okay, in the previous case, it was the intensity at the earth's S earth, which is given by power, total power, divided by area of the earth. Okay, and now this is the area of the sun. So we can write here is that P total divided by, what is the area of the sun? 4 pi r square. We know that this is the sun, and then we know the fixed radius r is known, 4 pi r square, where r sun here, and r sun is the radius of a sun. So can we plug in the values? What is the total power? Total power we just calculated in the previous slide. Here it is 3.93 into 10 to the power 3.93 into 10 to the power 26 watts divided by 4 pi, and radius of the sun, again the fixed number we know from the general knowledge, 6.96 into 10 to the power 8, and you square that because it's r square, and that comes out to be 6.42 into 10 to the power 7 watt per meter square. So you can say that this is the intensity of electromagnetic waves at the sun's surface, right here. This is the sun's surface. This is the sun's surface. Okay, this is the surface from which the waves are emitted in all directions. The radiation goes. So can we compare this number with the previous number? So S sun is about 6.42 into 10 to the power 7 watt per meter square. This is the first formula. And S earth the same waves which are reaching the earth have the intensity about 3.93 into 10 to the power 26 actually. Okay, this is watts per meter square. Okay, so it is like 3.93 into 10 to the power 26 watt per meter square. So we actually see that the intensity at the earth is no, let me correct it. This is not watt per meter square. It is actually the watts, because this is your total power, not the sun's not the intensity. This is the P total. Okay, we calculated the P total, which is S times the area of the sphere, area of the earth, that we actually wanted to calculate. Okay, so don't get confused here. P total, that is the total power, and S was this one, 1319 watt per meter square. So right here, yeah, just here 1390 watt per meter square. So imagine this is just like the rays reaching onto the earth's surface. Here somewhere your earth is, and those rays, the intensity of those waves is about 1.3 kilowatt per meter square. So in the 1 meter square area of the earth, the rays that reach the earth's surface will have such intensity, watt per such power, like 1.3 kilowatt. But at the sun, it's a big number, 10 to the power 7 watt per meter square. So in that area. Okay. So how about, instead of a meter square, like this is a meter, 1 meter, and this is also 1 meter. That's the spot or area of on the earth or on the sun. And these are the values of the intensities. But let's say on the earth, we have very small area, and we call it as a spot. And that area of that spot is receiving the sun rays. Okay, so let's say that area has a circular area, and that has a radius r is about 0.5 millimeter. So it's not a meter square, it's rather millimeter square area of that spot will be. So imagine the sun is right here. We'll take an example right here. Just give me a moment. So we are going to calculate the intensity of the electromagnetic waves at a particular spot on the earth when it receives the sun radiation. So let us draw this with the conceptual figure. This is your sun, and it has your radiation emitted in all direction right here. These are the radiations. And now I am having the earth's surface. This is your earth. Okay, and we have this little spot here. Just like you do your experiment with the magnifying glass, you go out in the atmosphere, in your garden or whatever, and you have a magnifying lens in your hand. In your childhood, you must have done this experiment. You take that magnifying glass onto a certain object, let's say ant or some plant or any spot, and on that spot you have your magnifying lens, which is of circular shape, and those that sun radiations are being received right here, okay, by this. Let me draw this well. So you have those radiations being received by this, and because of this lens, those radiations or the waves get intensified, and they are focused onto this particular spot. And let's say the area of this spot, I just told you, let us define it as a spot. Okay. So your lens is circular in nature, and we want to calculate, or let's say determine intensity S at this area of the spot. So it will be called as intensity at the spot. So this formula again, intensity at the spot would be power, total power, that is at the spot divided by the area of that spot. So it is, power is nothing but intensity of the rays that is coming onto the earth multiplied by the area of the lens, because now the lens is covering those rays, because up to the lens there is a lot of radiation coming, but through the lens these intensity is changing. So this will be the formula, and then you have area of the spot. So let us say area of the spot would be pi r square, because let's say we are saying that this is the circular area, simple, just a point there, and r is, let's say, 0.5 millimeter. So pi r square will give us a spot. Second, let's calculate area of lens. So let's say area lens is, you know that it is about few centimeters in radius. So a lens would be again pi r square, where r is the radius of a length, and that, let's say, imagine it is about 0.09 meter square. So that's the area I calculated, assuming that it has a radius of certain centimeters, few centimeters, and taking r square will give us. And we know that as Earth, what is the number? Can you remember what is the number? Number is here. Intensity of the sun reaching at the Earth is the fixed number, 1319 watt per meter square. So it would be 1319 meter square, watt per meter square. Watt per meter square. So with that, we can simply plug in this value. Therefore, the spot intensity at the spot of EM waves, it would be SEAR, that is the intensity of the rays reaching at the earth multiplied by the area of lens divided by the area of the spot. This is the formula. Again, focus on that. And that is equal to 1390 multiplied by area of lens is 0.09 meter square divided by pi multiplied by r square. R is your 0.5 mm. So 5 into 10 to the power minus 4. And you have to take the square. And that comes out to be about 1.6 multiplied by 10 to the power 8 watt per meter square. So now compare this number. This is the intensity of the EM wave reaching at this spot. You see, these rays came from the sun. It went through the magnifying glass, and after the focus, those rays got gathered here. And at this spot, the intensity is 1.10 to the power, 1.6 into 10 to the power 8 with watts per meter square. Can we compare this number with the intensity of the rays at the sun, which is 6.42 into 10 to the power 7 watt per meter square. So approximately of the same order. This is much bigger. So this is the intensity of the EM waves at a spot on the earth, this number. This is the intensity of the sun at its surface, the intensity of EM waves at its surface, at the sun's surface, and intensity of the sun at the earth's surface is very less, 1319 watt per meter square. So imagine 1390 watt per meter square is the intensity of EM waves at the earth's surface. But if we held a magnifying glass, look, compare this number. About 7 orders high if we pass those rays through the magnifying glass. So that was the topic about EM wave intensity. We'll use those formulas when we discuss another topics. And these are crucial formulas that need to be remembered. But the actual purpose of this module is to help you understand what is the total power of the sun, what is the intensity of EM waves coming at the earth, at the sun, and if we try to understand the intensity of EM waves at a particular point in a given surface, then we can calculate using those formulas.